For over a century, our understanding of metals has rested on a single, intuitive image: electrons acting like tiny pool balls, bouncing through a lattice while carrying both thermal energy and electric charge. Because the same particles are responsible for both, their flows are mathematically tethered. In a standard metal, any scattering process that blocks the flow of electricity will inevitably impede the flow of heat in the exact same proportion. This proportional lock is known as the Wiedemann-Franz law. It is the defining rule of quasi-particle physics, serving as a primary piece of evidence for the idea that space and the materials within it behave as a smooth, continuous medium. That assumption of a continuous fabric has held up across a century of experimentation. But that consistency completely ends when we look at the specific high-purity environment of a single layer of carbon atoms. To find the break, researchers look at ultra-clean graphene at the Dirac point, a state of perfect charge neutrality named after Paul Dirac, where the material's electron and hole branches are nearly symmetric. At this precise point, the electronic system stops behaving like a collection of independent particles. Instead, these electrons and holes begin to interact so strongly that they form a single collective fluid. In this fluid regime, the ratio of heat to electrical conductivity, the Lorentz ratio, spikes to more than 200 times the value allowed by the Wiedemann-Franz law. The two currents, previously locked together, have completely decoupled. Standard models attempt to explain this as a hydrodynamic quirk, a specific complexity of electron-hole collisions that happens to mask the underlying continuous physics. But when a foundational law of the continuum fails by a factor of 200, it forces a different question. Is this just a material anomaly, or have we found a scale where the assumption of continuous space itself no longer holds? The tetrasphere interpretation approaches this data by abandoning the smooth continuum entirely, proposing instead that the graphene is revealing the discrete structure of the vacuum. In this model, space is a rigid lattice built from discrete tetrahedral units. Motion here isn't smooth travel, it's the transfer of discrete tokens from node to node. Every update follows a synchronized cycle, making physical laws a product of token accounting. This means the laws we observe in metals are actually macroscopic illusions, approximations that only emerge when billions of these discrete token transfers are averaged out. When we apply this grid logic to graphene, the decoupling of heat and charge becomes a structural requirement rather than a mystery. Charge is a signed current. Positive and negative tokens moving in opposite directions create massive congestion, a parity drag bottlenecking electrical flow. But heat is unsigned. Both branches cooperate in the same direction, allowing the heat current to glide through the lattice unimpeded. This is why the Lorentz ratio explodes by a factor of 200. The grid's geometry creates a high-friction environment for opposing electrical tokens, while offering a low-resistance path for heat. The 200-fold jump in the Lorentz ratio is only the first piece of evidence. The experiment also revealed specific mathematical signatures that match the limits of a computing grid. Across multiple devices with different levels of disorder, the electrical conductivity converged to a single precise value, approximately 4e squared over h. This universal number represents a closure class invariant, the fixed token budget required for the lattice to process a specific mode of transport. It's a limit set by the grid itself, not the material. Combined with a viscosity to entropy ratio that approaches the theoretical minimum, the data suggests the fluid is moving along a path of near-zero computational burden. These aren't just properties of carbon atoms. They are the measurable bandwidth limits of the underlying system that processes the motion of matter. In ordinary metals, impurities and defects force these distinct token channels to lock together, creating the appearance of a smooth, continuous flow. Ultra-clean graphene functions as a rendered laboratory. Its extreme purity removes the noise of material defects, allowing the underlying mechanics of token transport to finally become visible to our instruments. When we account for the 200-fold spike in the Lorentz ratio, the universal conductivity, and the minimal viscosity, the model of a smooth continuum begins to look like an incomplete description. By providing a single geometric explanation for these anomalies, the graphene Dirac fluid offers more than just a material curiosity. It provides the first data-driven view of a universe that is discrete, computable, and tetrahedral.